with and that you dealt with in introductory E&M class derived from these equations. So we want to write these equations in a different way using something called potentials, which will be a very powerful formulation later on in the course. So from Calc 3, this is a Calc 3 statement. So this del, this operator, dotted by the cross. What I mean by cross product is if I have x, y, z, so del cross, so del cross E is just dx dy. Wow, we are running slow on time. Okay. So we take so for the x component, it's just dy dv minus dx dy x, and then you could just you'll just repeat this process going on. So you get a vector that's perpendicular to the plane. So if you have A cross B, you get and this is A, B, you get the vector perpendicular. You provide that. So this is a Calc 3 identity. So we could write the magnetic field just in terms of this. So B equals del cross A. So you write in that potential. So we could write the electric field in potential form as well, where you just take the gradient of the electric potential minus the time derivative of the magnetic potential. As you see, these satisfy Maxwell's equation. So this satisfies this Maxwell equation, 4. It satisfies 4. This one satisfies 2, because if you take the cross of this just goes to 0, and then equals minus del cross A over dt. That's just B, so minus del B dt. So these satisfy the non-homogeneous Maxwell equations. So let's see what we get when we satisfy the homogeneous or the non-homogeneous equations with 1 and 3. So if we plug in these potentials for number 1, we get E, so del dot E equals minus dt squared minus del T A, del dot A. So now we're gonna plug equals rho E naught. Now we're gonna plug it in for 3. So del cross B is just del cross A equals 1 over C squared. Plugging in E, we get minus time derivative of phi minus second time derivative A plus mu naught J. And by Calc 3, another identity of Calc 3 is this gives rise to this expression. So now I'm going to rewrite the equations 1 and 3. We're going to negate both sides. So we get del squared phi plus d dt of phi A equals minus rho now. And then number 3, we're going to rewrite this as So let's bring this over to the side. we get, and we're going to negate both sides, so plus to plus minus. So now we get del squared A minus. Yeah, this is sorry, this is a lot of algebra. I just want to be mathematically concise. So it's del A. Okay, so we have these two expressions. Now, what's nice about these potentials, why we want to introduce these potentials, is because it gives rise to a redundancy in the theory, or it gives some freedom to the theory, because we could replace one of these potentials. We could just add a constant to one of these potentials, or a field. We could change these potentials by the amount lambda, and we still get the Maxwell's equations remain the same. And you could try plugging it in. You know, we have our two fields represented by the vector potentials. So let's try plugging these in. You just get minus 5 minus d by dt lambda minus d by dt a minus. And so when we distribute these to here, to here, to here, to here, what we end up getting is these two terms cancel out, and we get back our equation for the electric field. So there's some redundancy. This is called gauge invariance. So we are going to use this gauge invariance to our advantage by choosing what's called a gauge condition. And we're going to impose this on the theory. So there's some redundancy that we could take advantage of to make this theory, to give us the results that we want, to make it more nice. So we'll see this right now. So we have these two equations. Oh, they look very messy, they look nasty. So, actually this is going to be our new, the one we're going to use. So we have these two.